Okay, hello everyone. Welcome back to Physics 3150. Let's go ahead and get started with our lecture today. So last time we started talking about, we continued our discussion on sequential circuits. We started talking about state machines and state diagrams, and we solved an example. We saw that how we can combine combinational logic and sequential logic in a way that we can detect certain sequences, right? So we said that like generally for these kind of systems, we have a sequential section, a sequential logic section, which has a bunch of flip-flops in there. The output of these flip-flops, we call it the current state. We can basically have multiple outputs here. Let's call them Z1, Z2, all the way to Zn. So based on the current state, we might actually raise a flag or not. And then these current states also form or like basically determine the next state together with some inputs. So the inputs W1 all the way to Wn, and then the current state also should come back here, right? So this was the entire system and how it looks like, and we talked about the fact that like we saw an example of detecting a sequence of, for example, we saw the example of detecting 101 sequence, and we're going to do another example today. But generally, this is good for any kind of, basically, if you want to design a system that has a bunch of inputs, bunch of outputs, and then it doesn't have a single state. For example, imagine that you want to design an elevator for a 2-story or 3-story building, and and then basically the inputs to the system is going to be basically the buttons that people are going to press at different floors. The output is going to be basically the number of floor that you're displaying on some display, and opening and closing the door and things like that. And the states are going to be basically, you could have many states in that situation, because, well, if the elevator is standing still in one floor, if it's moving up, moving down, moving up between floor 1 and 2 or 2 and 3, and then the inputs are basically it's not just the buttons, like it is the buttons, but then the buttons could have different kind of meaning. So basically, if a person pressed the button to go up at the main floor, or to press the button to go down at the second floor or third floor, they mean different things. So we have to call them W1, W2, all the way to, well, Wn, right? So an elevator would be a really nice example of these kind of sequential circuits, that you have to actually design the logic. You have many states, several inputs, and then outputs could be anything. Outputs could be basically commanding the door to open or close, or basically you have 7-segment displays that you want to show the floor that the elevator is currently at, or basically an LED display showing that the elevator is going up or going down, and things like that, right? So those are the kind of outputs that you want to generate. Another example would be a garage door opener, right? So like, for example, it's a very simple system if you think about it, but then if you look into details and you want to actually implement it, you can think about it that, for example, if the garage door is actually at the full open position or full closed position, or closing or opening, and then depending on these 4 states, you press your remote button to open the door or to close the door, or like if it detects an object as it is closing, what it should do, like it basically should have a sensor there, so that if it is closing and there's an object, it stops closing, pauses, or opens, goes back to the open position. So there's so many different kind of situations that you can imagine, but these are 2 real world examples to show you that any system that you want to design that has a bunch of sequences, you have a bunch of states, and then these states, you might go from one state to another if some condition happens. You're going to need these state machines, and then once you actually start drawing these state diagrams, it's kind of like you have the flow chart of your system. So we saw last time that we had a state diagram that had 4 different states, A, B, C and D. A was before we saw the first one, B was after we saw the first one, then C was 1 0, and then D was when we saw 1 0 1, right? And then we saw that, like, for example, if I see a 1 and then I see a 0 again, I'm gonna go back to A. But if I see a 1 0 and I see another 1, well, I go to D. If I see a 0, I go back to A, right? But here at D, if I see a 0, it's almost like I've seen a 1 and a 0, right? This is the 1, and then if I see a 0, it's kind of like I go back to C. I don't go back to A. And then if I see another 1, I go back to B, because it's almost like I have seen the first 1, right? So it's almost like basically I have 3 positions, and initially, if I'm at A, if I see a 0, I'm going to stay here. Initially, let's say that I have 0 0 0. Now what happens is that when the next bit comes in, imagine that everything is being shifted to the left. When the next bit comes in, let's say if it's a 1, I'm going to shoot out this 0, this is going to come here, this is going to come here, and then I'm going to bring the 1 here, right? So I'm going to have a 0 0 1. That means I have had the first 1. Now if I get if the next bit is 0 and the next bit is 1, I'm going to get a 1 0 1, right? Or for example, let's say I'm at state D, which is a 1 0 1, right? So if I get a 0, what happens is that, well, this guy is going to be discarded. So this goes here. I'm going to get a 0. This is a 1. Now if I get a 0, I'm going to get a 0 1 0, right? Now the reason that I say this goes to the state C, as I've shown here, if I get a 0 here, is that I'm at this state that if the next bit is 1, if the incoming bit in the next, let's say, clock cycle is 1, then this goes here, this goes there, and I have a chance of, if it is 1, sorry, this would be a 0. If it is 1, it would be a 1 0 1, which I'm going back to D. So I don't reset, I don't go back all the way to the state A. I'm just going to the state that I have seen a 1 and a 0, and I'm waiting for the next one. Now if I get a 0 at this point, so if it is a 1, I go back to state D. But if I get a 0 at this point, I'm gonna have a 1 0 0, right? Now in the next clock, this 0 is gonna come here again. This is gonna go away. This 0 is gonna come there, and then I'm at the position that I was at state A. I haven't seen my first 0 yet. It's the first 1 yet, right? So I'm still waiting for the first sign of my pattern to happen. If I'm expecting to see a 1 0 1, the first sign of my pattern is a 1, right? So if here is 0, I'm going to be staying at my state A. That's how I show it. And if it is a 1, I'm going to go to state B, which is a 0 0 1, which is basically I have seen my first 1. Okay, so we're going to solve another example today. We finished the last lecture with basically me telling you guys that please go ahead and do this homework, that if I want to detect the pattern of 1 1 0 1 or 1 0 1 1, how do I design my system? Then basically I ask you guys to actually do this. So today we're going to start our lecture with that. But then the important thing is that, as I mentioned, for every real world application that has any kind of like basically situation that we have a bunch of states, and we can transition between these states depending on the inputs and the current state, such as the controller for the elevator, controller for the garage door opener, or like you can imagine, controller for everything, right? For anything that you want to design that has a control system, you need to have a logic. You have to implement a logic. So the first thing you want to do is to draw the state diagram, and then we convert this to a transition table where you put your y prime and output here, and this is for w equal to 0, w equal to 1, and then you write down your states. Okay, And then from here, so this is step 2. From here we go to Carnot maps. So for each of these states, so if it's a 3-bit state, you need 3 Carnot maps, right? Which each of them have 3 bits plus 1 from the input, so 4 inputs, so it's going to be a 4x4 Carnot map. So we go from here to Carnot maps, and then from Carnot maps we know how to, we actually go and build this circuit. So this would be step 4. So through this step-by-step kind of a procedure, you can actually implement any kind of controller using real logic circuits, using real AND gates and OR gates and flip-flops. So you can implement that into any kind of a microprocessor or microcontroller, or like even a custom kind of a controller that you can implement on chip. Okay, let's start talking about the example that we want to solve. We want to detect a 1101 or a 1011. The first step, as we said, is to actually do this state diagram. So let's say that I'm at state, the first state that I'm going to define is state A. I'm going to say state A is really, well, the state that I'm still waiting to see the first one, because for both of my patterns, I'm going to need a 1 to actually get started, right? So as long as W is 0, as long as the input is 0, again, just imagine that you have this 4 position thing that you have to fill up. So right now you're at 0, 0, 0, 0. For the last 4 clock cycles, you've got just zeros. The moment you get a 1, it's the first sign that you might actually be able to create this 4-bit pattern, right? So let's call that state B. State B is the state that I have seen my first 1. So that's the definition of the state B. Now from this point forward, we can go either, like if I get a 0 or 1, I'm still happy. Why? Because if I get a 1, it looks like that I'm still on my way to make this pattern. If I get a 0, it looks like that I'm on my way to make this pattern. So let's say that I get a 1 and I'm on this way. So W is equal to 1. I go to state C. Now, if I get very lucky and the next thing is actually 0, then it means that I'm still on my way to that pattern. So I go to state D. So state C, the definition of state C is the state that the last two bits have been 1 and 1, right? And then state D is basically is the state that the last 3 bits have been 1, 1, 0, right? So that's state D. And then for state E, if I'm really lucky, then I might actually get W. If I get the W equal to 1, I go to state E where my output is 1. For all these things, all the other states, the output is 0. Okay. Now things might be a little bit different at state B. When I get to state B, which basically is the state that I've seen my first one, if I get a 0, W is equal to 0, and let's say that's the state that I've seen. The last 4 bits that I've seen has been 1, 0, 0, 1, 0, right? So that's the definition of state E. I've seen a 1, 0, so let's call that state F. And then if things are going well for me, I'm gonna get another 1. So F goes to G, and then if I get another 1, I'm gonna go to state H, which is again another state with an output of 1. Okay, so I have all my states, but you can imagine that, well, this is not the only thing that is happening. This is the best case scenario, that I only get the inputs that end up with either of these two patterns, so I'm going to be happy. But then so many other things might happen along the way, and we have to consider all of that, and we're going to do that, right? So up to now we have 8 states. We might actually go up to, like, I don't know, 15 states. So let's see that if we need more states, or like what will happen. The way that we have to consider all different possibilities is that Well, in each state that we currently have, we might have from that at that point, for every state that you can imagine yourself to be, you might get an input that is 0, or you might get an input that is 1. There's nothing else that might happen, right? So for state B, for example, we've considered both of those scenarios because both of them were actually good for us. But then for any other state, we didn't actually consider one or both of the inputs. Like for example, for state F, we only considered what happens if I get a W equal to 1. But we didn't consider what will happen if I get a W equal to 0. For state E or H, we didn't consider anything. Like we didn't consider if I get a W equal to 0 or 1 at this point, right? So this is the question that we have to answer right now. So let's get started from state A, right? For state A, we actually considered both of them. We said that state A was the state that I've been getting zeros for a long time, and I'm still getting zeros. So if I get a 0, I'm going to be staying at state A. If I get a 1, I go to state B. So there's nothing else we discussed about state A, right? How about state B? For state B, if I get a 0, well, B is also discussed fully. Let's go to state C. For state C, if I get a W equal to 0, I go to state D. I've already shown that. But then what will happen if I get another 1? So let's consider that. State C is basically the state that I start from state A, which was 0, 0, 0, 0. Then I got a 1, so it became 0, 0, 0, 1. Then I got another 1, it became 0, 0, 1, 1. Now I'm saying that what will happen if I get another 1? So this was state B, this was state C. If I get another 1, it's going to be 0, 1, 1, 1. Okay, so is this state a new state, or is it something that you can relate to? So if you think about it, when I was at state C, I was hoping that if the next two bits are going to be a 0 and a 1, then this 0, 1, 1, 0, 0, 1, 1 is going to be 1. The two ones are going to shift to the left. I'm going to get 1, 1 because it's been 2 bits coming in. And then I'm going to get a 0, 1, and then I'm going to be happy because it's one of the patterns that I like. Well, if you think about it, when I'm at 0, 1, 1, 1, I'm exactly at the same situation. Because if I get a 0, 1, right, as like if I get a 0 as the next bit, I'm going to go from here to 1, 1, 1, 0. And then if I get a 1 after that, I'm going to go to 1, 1, 0, 1. Everything shifting to the left. And I'm going to be happy. So it looks like that I'm exactly at the same state that I was before. So if I get a 1 here, I'm just going to stay at state C. How about state D? So you're going to, like, this might be a little bit confusing, but if we actually discuss this for all the states, bear with me, you're going to understand what's going on if you don't already. So state D, we saw that state D is, let me actually delete all this stuff. So state C was 0, 0, 1, 1, and state D is 0, 1, 1, 0. So this is the state that I only need a 1 to get to the good state E, which is basically the output becomes 1. But what will happen if I get a 0? Well, if I get a 0, I'm going to go to 1, 1, 0, 0. So these are the last 4 bits that I've seen. So can I relate to this? Well, looking at this, I can see that I cannot make any, like, I don't have any partial part of any of my patterns. It's almost like the last 2 bits that I've got is 0, 0, or last 3 bits is a 1, 0, 0. There's no way that I'm like partially on my way to basically this pattern or that pattern, right? So if I'm not partially on my way, it's almost like I'm waiting. I've resetted myself and I'm waiting for the first one to happen. So that's why if at state D, if I get a 0, I go all the way back to state A. Okay, how about state F? So looking at state F, I've discussed what will happen if I get a W equal to 1. So state F is a state that I have had the 0, 0, 1, 0. The last 2 bits that I've seen is a 1, 0 from state A. So this is state F. Now if I get a 1, yes, of course I'm gonna go to 0 0 1, sorry, to 0 1 0 1, which basically state G, that if I get another 1, I'm gonna go to 1 0 1 1, which I like. State H, I'm happy. But then what will happen if I get a 0? If I get a 0, I'm gonna go to 0 0, sorry, 0 1 0 0. Again, looking back at the last 4 bits, this is not something that I like. The last 3 bits is not helping me anyway with any of my patterns. Last 2 bits the same thing. So it looks like that I've resetted myself. So with state F, if I get a 0, I'm gonna go back to reset. How about state G? State G, if I get a, so state G is here, we've already discussed it. If I get a 1, I'm happy, I go to state H. But if I get a 0, I'm gonna go to 1 0 1 0. Now this is very interesting because it's looking back, this is not one of my patterns. Even looking at the last 3 bits, I can see that it's 0 1 0, it's not none of my patterns. But then last 2 bits is 1 0, right? If I add, if the next 2 bits are 1 1, meaning that if I ignore this and that, like if I throw them out and I add 2 1 1s to this, it's one of my patterns, right? So I'm halfway toward one of my patterns. Where is that halfway? Where is the state that I have received a 1 and a 0 and I'm waiting for 2 1s to come in? Well, it's the state F, right? State F was the state that I have received a 1 and a 0 and I'm waiting for the next 2 1s to come in, right? So for state G, I can say that if I get a 0, I actually go back to state F. I don't reset. I'm just basically, I have a 1 0 1 0. It's almost like I've received a 1, a 0, and I'm waiting for the next 2 1s to happen. Okay. The last 2 things that I have to look at. So we have discussed all different states. The only ones that are left are state E and H. Okay. State E was the state that I have seen a 1 1 0 1, and now what will happen if I get another 1? Well, if I get another 1, I'm gonna go from 1 1 0 1, I'm gonna throw out this 1, shift everything to the left, so I'm getting 1 0 1, and then add another 1 because that's my input, right? If I get a 1, I'm gonna get a 1 0 1 1. That's my state H. That's another pattern. So I'm extremely lucky here that if I get a 1, I just move to another state that is basically a state that I have a output of 1 here, right? Now, what will happen if I get a 0? If I get a 0, so from here, if I get a 0, then I still need to throw out that 1, and I get a 1 0 1. Then this time 0 comes here. So what is 1 0 1 0? We just discussed it up here. 1 0 1 0 is basically by itself is useless. Even 0 1 0 is useless. But then the last 2 bits, the 1 0 is the state that I've seen a 1 and a 0 and I'm waiting for the next 2 bits. So it's state F. So I'm going to say if I get W equal to 0, I'm going to go to state F. Okay. The last state is state H. So state H, looking at it, I can see that, okay, so state H is really 1 0 1 1, right? Now, if I get a 1, I'm going to throw this out. I'm going to have a 0 1 1 1, right? So this is not something that I like. Even the last 3 bits of 1 1 1 is not in none of my patterns, but the last 2 bits is a 1 1. That's the state where I've received the 2 1s, and then if I get another 0 and another 1, I'm gonna have a 1 1 0 1, which is the pattern one of the patterns that I'm looking for. So it looks like that from state H, if I get a 1, I'm gonna go directly to state C. How about if I get a 0? Well, if I get a 0, still I'm going to ignore this 1. I'm going to have 0, 1, 1, and then I'm going to add a 0. So the last 4 bits are nothing like one of my patterns. How about the last 3 bits? It's a 1, 1, 0. It's 1 bit away from one of my patterns. It's basically state D, where I had a 1, a 1, a 0, and if the next bit is 1, I'm going to state E, and I'm going to have my pattern built, right? So basically, from state H, I can say that I'm going to go directly to state D if I get a W equal to 0. And that's it. So if you think about it, for all of our 8 states, we didn't actually have to generate a new state. For all of our 8 states, we considered what will happen to that state, where do we go from that state if a W equal to 0 happens or a W equal to 1 happens. So there's no other possibility that could happen in the universe of the state machine or state diagram that we haven't considered yet. So we know all of the states, we have defined all of the states, and we've defined what will happen to these states. We have defined all the transitions, all the possible transitions. So we're done with our first step of our solution. From this point, we have to move on to the next step of the solution, where we talk about basically the transition table. Okay, for the transition table, all we need to do is to actually kind of translate what we have already drawn in the state diagram into a table format, right? So I'm going to have a table like this. This is the current state y. So like the first thing we notice is that we had 8 different states, A, B, C, D, E, F, G, H, and 8 states can be actually, because there are 8 different rows, we can represent them with 3 different bits, with 3 bits basically, right? And a 3-bit state has to be like the state has to be the states have to be represented with 3 bits. So I'm going to call it y2, y1, y0, and I'm going to say we're going to have all different numbers from 0 to 7. And I'm going to associate each of these numbers with one of my states. So I'm going to say this is state A, B, C, D, E, F, G, H. So now, do I have to call A000, or I can call A011 and B something else? Yes, I can if I just don't like myself. But like to make things easier, there's no reason to actually associate these things, these numbers, with these letters in the same order. There's no reason to actually have the order. Whatever way you do it, as long as each letter is associated with a unique 3-bit number, we're good. And then if basically you translate all the transitions correctly, you're not gonna have any problem. But then we're gonna do it this way because it's just gonna make our lives easier in terms of like converting this to a table and then from table to Carnot maps. Okay. So now the next state, said that we're going to show them with primes. So if W equal to 0, if W equal to 1, we're going to have 2 different scenarios. So y2 prime, y1 prime, y0 prime, y2 prime, y1 prime, y0 prime. So if W is equal to 0, for state A, we remain at A. So A is represented by 0, 0, 0, so I'm going to put 0, 0, 0. For W equal to 1, state A, I'm going to state B, which is 0, 0, 1. For B, for 0, I'm going to F, and for 1, I'm going to C. F is 1, 0, 1. C is 0, 1, 0. Right? For C, I'm going to D and C. So 0, 1, 1 and 0, 1, 0. For D, for W equal to 0 and 1, I'm going to A and E respectively. So A and E are 0, 0, 0. E is 1, 0, 0. Similarly, I'm going to go to, for E, we have F and H. So F is 101, H is 111. Oops, my pen started acting up, I guess. And for F, I have A and G. So 0, 0, 0, and G is 1, 1, 0. For G, I have F and H. So 1, 0, 1, and 1, 1, 1. And for H, I have D and C. So 0, 1, 1, and 0, 1, 0. Okay. And then the output is going to be Z. And I know that the output is going to be 1 only if I'm in state E or H. So E is going to be 1, H is going to be 1. For the rest of the states, I'm going to get a 0. Okay, I'm done with my transition table. The next step is the Carnot maps. So now I have to actually convert this table into Carnot maps. So we said that the Carnot maps are used to actually find out what is the relationship between the current state and the inputs and the next states. So first we're going to do the first Carnot maps that we're going to do is going to be for the Y2 prime, let's say. I'm going to need 3 Carnot maps because I have a 3-bit state. So this is, I'm going to say WY2, Y1, Y0. Even the order of these things is arbitrary, but I chose this because it's going to help us fill up the table or the map much easier. So let's say this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Now, and this is supposed to generate Y2 prime for me. So now if I want to fill up this map, I'm going to look at this and say, so first, the left hand side of the map is for W equal to 0. This is W equal to 1. Right? Looking at up here, I can see that, right? Now, if this is W equal to 0, so it means that the left column here, and I'm looking at only the bit that is associated with Y2 prime. So I'm talking about the most significant bit of this 3-bit number and the most significant bit of these 3-bit numbers. So looking at this, I know that the left one is supposed to be basically filling up those the left hand side of my Carnot map. Now the top of this left, the top 4 are for basically Y2 equal to 0. See, for the top 4, Y2 is equal to 0. For the bottom 4, Y2 is equal to 1. So this is the top 4 and this is the bottom 4. Okay. The only tricky thing is that you have to always remember you're doing 0, 0, 0, 0, 1, then 1, 1, and then 1, 0. So for example, here, for the first 4, I have a 0, 1, 0, 0. So I'm going to write it as 0, 1, and then 0 here, and then 0 here. For the next 4, I'm going to have a 1, 0, 1, 0. So it's going to be 1, 0, then 1, 0. Okay? The order is very important, otherwise you're going to get a completely wrong logic. You know that if one of these 1s and 0s in the Carnot maps, in the Carnot map is actually moved or like swapped, what happens is that like you're going to get a completely different logic expression. Then again, for this one, now we're talking about W equal to 1. So the right hand side of the table or the map, on the top we have Y2 equal to 0. Now this time remember Y2 equal to 0 is on the right because we have again 1, 0, and then here is 1, 1. So this 0, 0, 1, this 0, 0, 0, 1 is going to be here. So 0, 0, 0, 1. And then 1, 1, 1, 0 is going to be 1, 1, 1, 0. Okay. So now I'm going to be able to write my expression. It's not one of those easy Carnot maps. So I have this and this and this. And these two ones are just basically singular ones. I can't pair them up with anything else. So it's going to be an expression that is quite long. So it's going to be basically y2, y1 bar, y0 bar plus w, y2, oops, w, y2, y1 bar plus y1, y0 bar, y2 plus w bar, y2 bar, y1, y0 plus w, y2 bar, y1, y0. Okay, next one, we're going to do y1 prime. So same thing, we're going to do it quicker this time. W, y2, y1, y0. This is going to be y1 prime. Now, to fill up this thing, first let's put these numbers up there to help us along the way. Okay. Now, again, this time I'm looking at the second bit, so the middle bit in this state, and in the same order. So I'm going to have 0, 0, 1, 0. So 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. Then here, these four, I'm going to have 0, 1, 1, 0, 0, 1, 1, 0. And the last four is going to be 1, 1, 1, 1. Well, that's going to help us with the Carnot map. So this is good. And this one, and this one, and I guess this one, and this one. Okay. So now y1 bar, or y1 prime is going to be w y2 plus y1 bar y0 w plus y2 y1 y0 plus y2 bar y1 y0 bar. Okay, the last one for y0 prime, I'm just going to do the map. You can write the logic yourself. I guess it's going to be 0, 1, 0, 1. We're just looking at these four bits. So it's 0, 1, 1, 0. So it should be 0, 1, 1, 0. Then 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0, and 1, 0, 1, 0, 1, 0, 1, 0. Then you can imagine that you have this, and you have this, and that, and this and that, and I guess this is a singular one. And you can write the logic for that. Okay, so we're done with step 1, which was the transition table, and step 2, which was the Carnot maps. Okay, now we have the logic, and sorry, this was actually step 2, which was the transition table. Step 1 was the state machine or state diagram, and step 3 was Carnot maps. We're almost done with the final. So basically, all we need to do is to, like, there's one other thing that is left, which is basically the output. So the output Z. Again, we can do if you think about it, we can do a Carnot map for the Z as well. But there's no need to actually do that. We know that Z becomes 1 when it's E or H. So E is 1, 0, 0. So y2, y1 bar, y0 bar, or it's going to be y2, y1, y0. Okay, so it's just basically 2, 3 input AND gates, and then an OR gate connecting the outputs of the AND gates together. That would be my output. But if you liked, you could have done this. So you could have said, well, this is my y2, y1, and this is y0. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So I'm going to get a 1 when I have a y2 equal to 1, and then the other two are 0. So this is going to be this cell, and then I'm going to get a 1 when all of them are 1, so this cell. The rest of them are 0. And then you could have just drawn a circle around this and that and got to this expression. Okay, so this, I did this because not because we actually needed it, it's because if we actually had an example where Z was not as simple as this, you know that you can always do a Carnot map for the output as well. Okay, so now from the expressions that we got, we can easily draw the Carnot map. So like draw the state machine. So we say that I'm gonna have 3 flip-flops because my states are 3 bits. I have DQ, DQ, and DQ. These are the inputs. Oops, this was supposed to be the clock. So I'm gonna have 3 clocks here. And the clocks are connected to some clock signal coming in, and then the output is going to be called the current state. So let's call this y0, y1, y2. Again, this is random, so like you could have called any of them y0, y1, or y2. This is just makes sense. Or you could have done y2, y1, y0. There's nothing stopping us from doing that. Okay, and then for the output, let's do the easy one first. We know that it's going to be y0, y1, y2 added together, or with y2, y0 bar. So let's use another color. So y0 bar, y1 bar, and y2. These guys are added together too. So instead of these bubbles, I could have put an inverter. I hope all of you know that by now. Now I have 2 of these guys ORed with each other, and that would be my output. So Z becomes 1 only if this logic circuit is going to be giving me a 1. So this is going to be basically, this part is the second combinational circuit that we have been talking about. So let's call it combinational B, which basically gets this state and generates the output. Now for the other combinational circuit, you can imagine I'm not going to be drawing that huge logic, drawing circuits for those huge logic expressions, and I don't expect you guys to actually do that, except like if it's a very simple logic design. So basically we have a bunch of gates here. I guess all of you can implement sum of products with AND gates and OR gates, so I don't want you guys to actually draw them for us, but we know that W is coming in, and we know that I have feedback from y0, y1, and y2. And by feedback I mean this is actually connected to here, and this is actually connected to there, and this y0 is also connected to here. Okay, and then for each of these, so this is basically going to be y0 prime, this is going to be y1 prime, this is going to be y2 prime, and then from these inputs, these 4 inputs, W, Y0, Y1, and Y2, to get to Y0 prime, Y1 prime, and Y2 prime, we have to use the logic that we basically got from the Carnot maps. For example, for Y1 prime, we had W, Y2, so like basically we had a W and a Y2 added with each other. Then we had Y1 bar, Y0, W, so a 3 input AND gate. W, Y0, Y1 bar. Then we had Y2, Y1, Y0. Y2, Y1, Y0. And then also we had Y2 bar, Y1, Y0 bar. Y2 bar, Y1, Y0 bar. And then the output of all of these guys are going to be ORed with each other, and that will generate y1 prime for me. Okay, so this is basically only the logic that generates this y1 prime. So it gets all these 4 inputs, and then you use this circuit to get to y1 prime. You can do the same thing for y0 prime and y2 prime and get the logic.